Hello and welcome once again. In the upcoming two modules, we will discuss about some advanced plotting packages in R, which are Lattice and ggplot2. Previously as well, we have come across the basic plotting functions in R, but as we know, these had some disadvantages as well as some advantages. The Lattice and ggplot2 fills in those disadvantages. So here we have all the functionalities of these two packages. Primarily in this lecture we will concentrate on the package called Lattice. We will show you how some basic plots like histogram, frequency polygon, box plot and others are made using this package which is called Lattice. We will let you know how with the help of some default functions we can actually construct several plots which we could have been done using the basic plot functions but with enormous effort. So let's concentrate on what is there in this module. The learning objectives of the module are basic syntax of the plotting functions of Lattice, use of several well-known plotting functions, comparison with basic plot function. The package Lattice has been developed by Dipayan Sarkar. The book written by him enlighten us to grab some clear ideas regarding this package which is meant for advanced plotting. In this course, we are primarily following his book Multivariate Data Visualization with R. As the name of the book suggests, for multivariate data visualization, this is probably the best package to deal with, and this is perhaps the reason behind the popularity of this package. To start with, we are taking a very simple example. By now we have come across the empty curse data many a times. The data was extracted from the 1974 Motor Trend US magazine and comprises fuel consumption and 10 aspects of automobile design and performance for 32 automobiles which are primarily 1973 to 74 models. We all know that from the description of the data. Now at first, among all the variables, we are considering the two variables MPG, that is miles per gallon, and CYL, that is the number of cylinders. The first one, that is MPG, is a continuous variable, and the second one is a discrete variable which takes only 3 values. Now our objective is to have a histogram for a particular variable. We can do this using the simple plot functions as well, right? So what is special here? Let's see. Here we are considering the MPG variables corresponding to each of the 3 factors of CYL. So for this, here we are using the command that we have mentioned here, and look at the output that we are getting. This is primarily a collection of 3 histograms which we have for each of the 3 factors. Now have a closer look at the plot. Each histogram occupies a small rectangular area known as a panel. Here altogether we have 3 arrays. The dimension of these have been determined automatically since we have 3 factors, so we have 3 arrays. Another point to look at is that all the 3 panels share the same scales, and as we can understand, this makes the distributions easy to compare. Previously we have we also faced with these problems because the plotting function is not good enough to do that. A strip at the top of each panel describes which value of the score that the panel represents. These features are available in all Trellis displays and are collectively known as multi-panel conditioning. By default, this plot contains all these things, although one can always change the default settings and can use it according to their own convenience. Using the usual hist function, we can separately draw the histograms, right? But indeed that would lack the features which we are having here by default. That's what we are trying to say here. Now remember, a little while ago we coined the term trellis displays. So it's time to give some ideas regarding the trellis call. To know this, let us take a closer look at the histogram call. Now look at the arguments of it. It has two arguments. The first argument is a formula object that specifies the variables involved in the model. The second argument, that is data, which has a correspondence to the variables used. It borrows the variables from the data only. In the formula, factor CYL is a conditioning variable indicating that the resulting plot should contain one panel for each of its unique values of CYL. In the formula, the left panel consists of the primary variable that is involved in each of the panels, like the variable MPG here in case of empty curves dataset that we are considering. Now remember, a little while ago we coined the term trellis displays. So it's time to give some ideas regarding the trellis call. To know this, let us take a closer look at the histogram call. Now look at the arguments of it. It has two arguments. The first argument is a formula object that specifies the variables involved in the model. The second argument, that is data, which has a correspondence to the variables used. It borrows the variables from the data only. In the formula, factor CYL is a conditioning variable indicating that the resulting plot should contain one panel for each of its unique values of CYL. In the formula, the left panel consists of the primary variable that is involved in each of the panels, like the variable MPG here in case of empty curves dataset that we are considering. So look at the output that we are having here. Since we haven't specified any conditioning variable, so as we can guess, we have only one histogram here for the variable MPG. It's quite obvious. Here we will start the discussion of aspect ratio. So the question with which we will start the discussion is, what is aspect ratio? Primarily, the aspect ratio of a panel is the ratio of its physical height and width. Now the choice of it is very important and it acts effectively for displaying a plot. So the question now is how to choose it, and the simple answer is there is no conventional way of choosing this. So the quick solution that we adopt in most of the cases is by applying the trial and error method. Although many automatic selection procedures are always there for our convenience, but usually we prefer the trial and error ones. Have a look at the output that we are getting here using the R code that is given here. As the plots show, the display is dependent on the aspect ratio. Here one can do a number of experimentations with these values and might observe what happens. We try the values aspect is equal to 0.2 and 0.5 and let's see what happens. Indeed, we can go on experimenting with this as well. Another interesting point is that a good choice of layout needs to take the aspect ratio into account. We know that for the simple R plots, using the simple layout function, we can redirect the plot layouts. We have done this previously as well. Here in Lattice, we can have a number of examples where we will find that the default tunings are not using the available space. Although the package Lattice gives us a number of things even in default setup that we have claimed even in the introduction as well, but in some of the cases you need to customize the default setup. So things are not exactly the same always. A trellis display consists of several panels arranged in a rectangular array. The layout argument determines this arrangement. We have seen this for the plotting functions, basic plotting functions as well. If you want to have an exact specification, then it can be said that the layout should be numeric vector giving the number of columns, rows and pages in a multi-panel display.
If you want to specify the number of pages, then you can always do that, but if you don't, then the third element need not be specified. Then how does it work? Actually, it is chosen automatically to allow all the panels. Here it is worthy to mention that the Cartesian coordinate system is used where the panels are drawn starting from the lower left corner, proceeding first right and then up. So this is how it works. Now let's consider one of the most useful plots to visualize univariate distribution, which is a box plot. We know that two sample quantile plots can effectively compare two samples at a time, but only two. They do not generalize to more. Again, if you look at a matrix of pairwise quantile plot, then you will see that they compare multiple samples, but it has some limitations. It takes up too much of space and can be hard to interpret. So next is what? The next alternative is actually the box and whisker plot in Lattice, which has the potential to compare multiple samples. Here essentially each distribution is summarized by 5 quartiles, 3 quartiles that define the box and 2 extremes that define the whiskers. We know what is a box plot. So how will it work for the Lattice package? Lattice provides us a simple function called bwplot function, which is meant for constructing the box plots. Now let's start considering the M-29 example. As we know from the description of the data that it provides the score on the 1997 A-level chemistry examination in Britain. Here the students are grouped into schools within local education authorities. In addition, some demographic and pretest information is provided. It provides us GCSE score corresponding to a number of students that includes representatives from both the gender, male and female. Look at the R code that we have here and that produces box plot. This is the output plot and that we have got here. Here as we can see, for every level a box and whisker plot of the corresponding GCSE score values is drawn. This allows us to directly compare the median, which is the dot in black, and the 25th and the 75th quantiles. In some variants, what we see is that the whiskers extend to the minimum and maximum of the data, but conveniently they are limited to a multiple of the length of the box. Here also we can always experiment with the choices of the argument, varied, layout and many more. And changing the values of these arguments, one can actually observe how the plot changes. So this is what the box and whisker plot says. Another simple way of representing your data is through density plot, which is very important as well. As we know, density plot is something which allows us to have some idea regarding the actual distribution of a particular variable of the underlying data set. So have a look at the R code that we have given here. As you can see, this is the simplest form of representing the density. Here, as minimum as possible arguments are used. So for all the remaining arguments, the default settings have been used. So this is what we are trying to say, that using the default functions as well, we can have some excellent plots using the Lattice function. So have a look at the density plot that we are getting from here. Now we can always have these plots for each of the factor score by conditioning the primary variable with the conditioning variable factor score, as we have seen earlier as well. And by doing this, we are going to have 6 different plots corresponding to this. So have a look at the plots. Here, by looking at the plot, we can see that by default we are having the estimated density, and one more thing, which is the points that are plotted here in the diagram. Why the plots are needed? Why the points are needed? Primarily, it helps us to address overplotting and ties. Here also you can always experiment with these points as well. The plot.points argument can be used to change it to a rug or omit the points entirely. So let's try to explore what these plot.points do. Have a look at the R code that we are given here. Here one additional argument is provided, and that is plot.points argument. Here if we want to eliminate all the points, then we need to use this plot.points is equal to false. And look at the plots that we are getting here. Compare the plot with the previous one. The only difference here is that the points have been eliminated. And again, if we put plot.points is equal to rug, then we are going to have a plot like the following. So look at the plot that we have got using plot.points equal to rug. You can do many more things using the density plot function. Look at the R code here. It is primarily a grouped density plot. By this, what we mean is, here we have specified groups equal to gender. So here what the function does is, it makes two different plots based on the two genders for each of the 6 scores. We can do this grouping based on any other grouping variables as well, as we can understand this. So look at the output that we are getting here. By default, 2 different colors are used to differentiate between the 2 groups. Here comes the idea of using the auto.key option. Why is it needed? It helps us to put one of the important feature of a plot, which is the legend. This allows for more convenient defaults, and one of the advantages here is that it is usually possible to omit the text component as well as the points, lines, rectangles, these components as well. One can simply use the auto.key is equal to list space is equal to right in the above call, or even auto.key is equal to true, which would use the default space is equal to top. So it will put the legend in the top. So here is the R code. If you compare this with that of the previous one, then we may observe the legend which is there in the top of the plot. So look at the output. We have obtained this using the default setting. But if we use space equals right, then we will have the next plot that is given here. Now let us do some experimentation with the column option of the auto.key argument. Put column equals 1 and 2 here and observe what is happening here. Have a look at the 2 plots and spot the difference between the position of the legends of the 2 plots. You can specify only 1 and 2 in this column argument, as 1 suggests that the legends will be arranged in a column, while 2 is for the arrangement in 2 columns. As we have said a little while ago, we can set the positioning with the space option as well. So there are rooms for a lot of experimentations in this regard, as we can see. Now suppose you are not happy with the colors of the 2 densities and you wish to change it to some other colors according to your wish. Then what will you do? Additionally, one more problem is, how will you memorize all the default settings? Here comes the solution. Just type show.settings and look at the things that we have obtained. All the plotting functions do not give us these facilities, so this is another advantage of this plotting function. So life becomes easier when you use these kinds of specified packages. Now suppose you wish to take the printout of these in a black and white printer. So you might be thinking that this is not possible since this would disrupt the entire settings. But things are not like that. If you write down standard.theme color is equal to false within the bracket of show.settings, then that would give you the default, that would change the default settings in grayscale. So now you can take out the printouts with lesser hazards. So this is what the default settings are, but the question is, can we change the default setting? The answer is yes. Suppose we want to change the theme into green and blue. So here we are specifying our desired color in the COL option within the simple theme and storing it to CNG. Now if we want to see the transformed settings, then we need to type show.settings, then within the first bracket CNG, where the changed version has been stored. Now look at the output that we are getting here, as shows the transformed settings that we wished for. So now let's try to find the ways to apply this setting that we have just made. We have made it to apply it for here, right? To change the group colors, one just needs to change the part.settings argument. Here, since we have stored the transformed details in CNG, so here we are specifying part.settings equals CNG, and then we are tuning the other argument of the density plot function based on the argument gathered so far. So on the basis of this setting, look at the output that we are getting. Here, as we can observe, the output is displayed using blue and green colors that we desired for, and this is because of the changed setting that we did a little while ago. The next type of plot that we will be discussing here is the dot plot. It is introduced by Cleveland in 1985 and provides simple and effective graphical summaries of tables. These kinds of plots are less often used, but indeed it has a potential of a broader use. Let's consider the VA dataset to illustrate what we are trying to say here. As you can see, this dataset gives us the death rates of individuals for each of the age groups. Here we have 4 subgroups for each of the age groups, that is rural male, rural female, urban male and urban female, for which the data have been collected. So this is what the data description is. Look at the R code. Here we are using all the other default settings, and along with that we are using default equals false. And look at the output that we are having here. These are primarily dot plots of death rates cross tabulated by age and demographic groups. Now have a look at the next one. Here we have considered the things from a slightly different point of view. Here, for our convenience, VAD has been built up and we are considering the variables, age group and deaths for each of the subcategories like rural male, rural female, urban male and urban female. And this is what the output dot plot says. Interestingly, the VA deaths object is of class matrix. One can find this just by typing class of VA deaths. Also here we can check the available methods for the dot plot function. But how do we check that? We can always check it by typing methods within first bracket within inverted commas dot plot, and look at the output that we are having. The interesting point is that the dot plots can be saved as R objects. Not only the dot plots, all the plots. Here comes the idea of saving and updating an R plot. Here we have stored the plot within the R object SV, and we can always call the object by writing SV. Also we can change the details of the R object that we have specified at the time of saving. Like here, the first plot contains line as well as the points, but later on we want a plot that contains only lines, no points, because the points would make it more clumsy. So here are the two plots. As one can see, the first one contains both lines and points, but the second one contains only lines. Here we have a summary of the functions used in Lattice. This is needless to say that using simple plot function, one will not be able to represent these things effortlessly.
So as we have seen in this module, the Lattice package is probably one of the best packages in terms of multivariate data visualization in R. With the help of several examples, we have come across the functionalities of this package, and we have seen how with the help of the default functions we can have several advanced plottings in R. We have seen how the overall appearances of the curves can be changed with the help of the parameters, with the help of the parameters in the Lattice package, and also how we can have better control on the parameters of the plotting functions. So let's stop here, and as we have said that in the next module we will discuss about another advanced plotting function, which is ggplot2, and with the help of several examples we will let you know the advantages and disadvantages of using that function.